This is the Heathkit model ET-3400. It's known as the Microcomputer learning system, but also as the Microcomputer or Microprocessor Trainer, as you can see on this reproduction of the original manual. If we bring the device out of standby, you'll see its own iconic CPU up message. The Heath company was a major provider of electronic kits to hobbyists through the 1950s, 60s, 70s and 80s, and they also provided a lot of educational course material to go with their training products. The ET-3400 is one of those training solutions and is based on the Motorola 6800 processor. The ET-3400 was first advertised in the Christmas 1977 edition of the Heathkit catalogue. There are a number of unsourced claims online indicating a 1976 release date. And it's certainly possible Heathkit had retail stores. However, the 1977 catalogue appears to be the first appearance of the unit in print. While the ET-3400 was available as an assembled unit, many, including this one, would have come as kits. For that reason, they come with these comprehensive user manuals, and we can have a quick flick through this one to have a look inside. You can see details of the parts that were required and how to assemble them onto the various parts of the circuit board. Lots of comprehensive detail for the beginning assembler. I'll provide a link to this manual for you to download if you'd like to take a look. The first example program in the manual is this sample 1, and its purpose is to turn on and off each segment in sequence on the displays. I've already gone ahead and entered the sample program into the computer's memory. This is possible because when the device is in standby, much of the circuitry remains powered, including the computer's RAM. We can inspect that memory by pressing the E button, and the computer then asks us which address we would like to examine. Let's start at 0000. Here we see BD in the first byte of memory. We can go forward by pressing the forward button. This brings us to memory address 1, which contains FC, and we can continue going forward and inspecting the memory locations. We can also press B to go backwards. To run the program, we press the Do button. It then asks us which address we'd like to start from. Let's try 0000. We can now see the segment test pattern looping round. As I mentioned, much of the circuitry remains powered when in standby, and in fact, the processor continues to run. We can demonstrate that by putting the machine in standby while this program is operating. As you can see, the pattern had clearly progressed, even though the displays were off, indicating the processor had not been halted. Now I've demonstrated the ET-3400, I'd like to walk you through a few of the repairs I've made to this particular device. While Heathkit did have retail stores and a distribution system in the UK, Heathkit products were much less popular than in the US. As such, while these devices are reasonably plentiful stateside, they're a little rarer on this side of the pond. This means that Heathkit products come up for sale in the UK far less frequently, and when they do, they are fairly expensive. Importing them from the United States is equally as costly. In my case, I actually ended up importing this device from the Republic of Ireland. This means that it was already configured for the 240V 50Hz power supply that we have here in the UK. While the device I purchased was shown as functional in the listing, it was a little worse for the wear, and in fact required a number of functional and cosmetic restorations. The most obvious cosmetic issue with the device, which had been pointed out by the seller, was the mismatched displays provided on the unit. When I received the device, it came with these 6 displays, and as we'll see, they probably came from 4 different sources. Most significantly, when I remove these, you'll be able to see that these top 3 displays here have much longer legs than these bottom 3. This was a problem because these top displays sat very proud of the socket, showing the displays at very different heights. If we look on the ends here, we can see that we have different colour grading for the different displays, and this one actually has a different typeface, although these are all graded F. These displays here are both graded E and are likely a matched pair. Finally, we have this very low profile display, which doesn't appear to be a Texas Instrument display at all. Notably, it also has the decimal places rather than side by side on the bottom of the display. It actually has 2 here stacked top on bottom. To make sure all the displays were the same, I went ahead and ordered 6 new old stock TIL-312 displays, and these are what we have installed in the unit today. When I received the replacements, they all look like this display here, and that's because they don't come with contrast enhancing film by default. The top three displays are featuring the original Heathkit provided contrast enhancing film. However, the bottom three displays didn't have any when I received them. You can see my experiments with these two left-hand displays. The first one is showing some tail light repair tape, and while this does work for enhancing the contrast, as you can see it's fairly opaque and therefore it leaves quite a red coloration to the face of the display. As an alternative, I tried some red window tint film, and this is what I ended up using and applied to the rest of the displays, as you can see in the unit. Another cosmetic change I made to the computer was with regard to these LEDs right here. A number of the LEDs were a different size and had a different coloration. As this device is aimed at experimenters, it's quite possible that various voltages were applied to the LEDs and some of them burnt out during use. These are the LEDs that were fitted when I received the device. You may be able to just make out that they have very slightly different profiles, but when illuminated they were significantly different colours. To rectify this, I went ahead and replaced all of the LEDs, but unfortunately you can't replace them with modern high brightness LEDs, as these will have a significantly different colour and brightness than the originals. Now, vintage LEDs can be rather expensive, and so it was actually more economical to go on Mouser and buy a variety of LEDs by different manufacturers with similar brightness and colour profiles. Eventually, I settled on these BioVar LEDs, the 5RD-F, and you can see those installed just here. Now, these do have a very slightly taller profile than the original LEDs, but at least I have matching examples now. Equally, they are marginally brighter than the originals, but this may just be an artifact of the original LED's aging. You can see the brightness of the LED as I went ahead and replaced this LED here as well with a matching LED, and that's to ensure that this is equally colour matched. Another cosmetic change I made was to rearrange some of the resistors on the circuit board. As you can see, my unit is a fairly early one with carbon composite resistors. However, a number of the resistors, particularly around the LEDs, had obviously failed, and so had been replaced by more modern carbon film examples. To ensure a consistent look, I scavenged appropriate carbon composite resistors from elsewhere on the circuit board and replaced them where we can see them on the face of the device. I then went ahead and replaced the now missing resistors with appropriately valued carbon film resistors in their inconspicuous locations. Also in this area of the circuit, you can see a switch for entering binary data. You can see the case itself is fairly well worn, and in fact one of the switch positions itself had been slightly worn and melted. You can see that original switch here, and what I've gone ahead and done is disassembled the switch, and I've replaced the contents of the switch unit with a newer version still from the same manufacturer, CTS, and I've reattached that to the board. You may be wondering why I left the original case in place, and that's because if you look closely, these CTS switches go from 1 to 8, which is very reasonable on regular DIP switches. However, the part on the board here is custom printed for Heathkit, going from 7 to 0, representing the binary bit positions. Finally, as a purely cosmetic change, I went ahead and replaced some of the RAM. The original ET-3400 would have been provided with 2 chips, although an additional 2 chips were available as an option. Here we have the 2 chips that I was provided when I purchased the unit, and you can see these are actually mismatched. Here we have a Japanese provider and one by AMD. These were both in the upper slot here. Now, while they were perfectly functional, I decided for cosmetic reasons I'd like a matched pair, and so I went ahead and bought some replacements. And while I have enough chips that I could replace all 4 of these to be a matched set, I feel it's appropriate to have mismatched in these 2 locations, as they would have been provided potentially at a later date, and I think it's nice to have some original 1977 RAM in the first 2 IC sockets here. When I received the unit, it was fairly grubby, and while I have cleaned it, it's not as clean as I would like. Unfortunately, the silkscreen printing on here does dissolve and smudge in alcohol. That means that I can't use isopropyl to clean the circuit board as I might have liked. When I was cleaning the device, I removed many of the chips, including the buffer at IC7. This is that original chip, and if you look closely, you can see it has extremely tarnished legs. So much so, in fact, that when I went to reinsert it, 4 of the legs detached from the device. Now, as you can see, I was able to solder on some replacement pins, and this chip is fully functional. However, I thought it would be best to replace it with a modern chip instead. Again, for aesthetic reasons, I rearranged the chips as IC1, 6, 7 and 8 are all of the same type to allow me to put the modern chip down here in the IC1 position. A more functional deficiency with the unit, that it was missing the solderless breadboard connection point here for the ground. While this didn't stop the computer from operating, it does mean that we couldn't carry out many of the experiments without an appropriate ground connection point. These 4-pin solderless breadboard connection blocks are extremely hard to source. So as an alternative, I scavenged the one from the RE line just here and moved it to the ground section. And as you can see, I've replaced the RE block here with a 2x4 pin available from Adafruit. The Adafruit block did require some modification to be useful for this purpose. Firstly, I had to remove the plastic plug pins as they didn't fit the board layout. And secondly, I had to short together the 4 independent sections into one single unit, as would have been more appropriate for the original. Once modified, I soldered the block in place and secured it with 2 tiny screws. This means that I can still access the RE line from the breadboard section on top of the device. While the Adafruit block has allowed me to restore the functionality of the device, it's clearly visually very anachronistic. So if any of my viewers happen to have spares of the 1x4 Heathkit block, I'd very much appreciate you getting in contact so one day I might be able to achieve a full restoration of this device. As a final cosmetic change to the device, I had to remove a few additional sockets from the board. But as you can see, there are no unpopulated areas. These are those additional sockets. As you can see, most of the board is populated with these white single wipe sockets, but the ROM and CPU are installed in turned pin, gold pin sockets. For whatever reason, each of these chips have been stacked inside these sockets and then inserted into another socket on the board. While this had no impact on the functionality, I thought it was a rather odd thing to do, and it visibly raised the level of the chips. So I've gone ahead and removed these additional sockets and have inserted the chips directly into the underlying identical turned pin gold sockets on the board. In addition to the visible changes I made to the computer, I had to make a few functional repairs to the device as well, and these are all hidden below the case. As an aside, we can see 2 different dates silk screened onto the board. At the bottom here, we can see the 17th of April 1977, but at the top, we can see the 13th of June 1977. As you can see, there's some additional circuitry hidden under this upper area of the unit. Firstly, when I received the unit, despite it showing CPU up in the advert, it was entirely non-functional. And this was actually a very basic issue. During shipping, one of the wires along the top here that provides power had become detached. On restoring that, the device was fully operational. Unfortunately, during the first few minutes of operation, the device would frequently crash. The device would either reset, show random characters along the display, or entirely lock up until the reset button was pressed. However, once the device had been on for a few minutes and warmed up, it became stable and in fact was able to operate continuously for hours at a time. By a process largely of elimination, I discovered that it was the clock generation chip just here on the board that was malfunctioning. When it was cold, it was not operating correctly, but once it warmed up, it became stable. Here I have the original chip, and this one's from the 25th week of 1977. You'll notice it is a 4 MHz part, and in this particular unit, we can see there is a 4 MHz crystal driving that clock chip. Now originally, the ET-3400 used a resistor and capacitor to drive the clock circuit. This has been modified with a 4 MHz crystal. In the later model ET-3400A version of the computer, you'll see there is a 4 MHz crystal visible right here in this location on the front of the board. This is matched with a version of the MC6800 that can drive the clock crystal directly, either an MC6802 or MC6808. Another functional issue with the computer was the lack of a 1 Hz or line frequency square wave on this block just here. Now this doesn't affect the operation of the computer, but it would prevent doing certain experiments on the breadboard area. This was due to the failure of this IC just here. And in this piece of foam here, I have the original IC. It's an LM2901, and it's actually one of the earliest chips in the entire unit. It's from 1976, week 52. On replacing the chip with a modern replacement, we then have a 1 Hz and line frequency signal on this block just here. I can show you that with a wire as follows. We can go ahead and connect the wire from the 1 Hz signal to the LED just here. And as you can see, it should pulse with approximately a 1 Hz frequency. I can of course try and pick up the line frequency as well. And unfortunately, we won't be able to see that because it's blinking faster than we can see. But if I go ahead and instead provide 5 volts to that LED, hopefully you'll be able to see that the brightness is somewhat different. If you're still not convinced though, we of course can go ahead and measure that with an oscilloscope. And as you may know, I recently assembled an oscilloscope in one of my videos. So let's see if we can do something useful with this mini oscilloscope after all. First up, of course, I need to connect the ground into my fully repaired ground block. And then I want to go ahead and pick up the 1 Hertz signal here. Let's pop this in like so. And if I go ahead and adjust the time base here to 500 milliseconds and give it a few seconds to update, hopefully we can see here we now have a 1 Hertz signal. Don't know if you can make that out on the camera. You'll see that it says fail here, and that's simply because the trigger point is failing to run, but that's not stopping it detecting the frequency of the circuit. Of course, more interestingly, we want to detect the line frequency, so I can move this over to the line frequency point. And of course, I'll need to adjust the time base. So if I can adjust this down to 10 milliseconds here, you can see it's reading 44 Hertz. Now, this is definitely incorrect, so this oscilloscope is indeed not precise. The UK power frequency is actually 50 Hertz, and it is pretty much bang on rock solid at all times. So this is an incorrect reading, but as you can see, there is a different square wave frequency coming out of that block. If I'd connected a more capable oscilloscope, we'd be able to see that 50 Hertz frequency much more clearly. You may have noticed one more chip here in the conductive foam, and that's the 7400. And this is a NAND gate. Now, I replaced this chip essentially for cosmetic reasons. This chip is fully functional as far as the computer operating is concerned. However, it used to sit in this socket here in IC21, and I've replaced it with a more modern replacement. If we look on the schematic here, we can see that IC21 is a NAND gate, and pins 9 and 10 are connected to bit 0 on the data bus. This presents a purely cosmetic problem for us if we attempt to read an unmapped area of the address space. In such a situation, the data bus may be left floating and will contain invalid data. However, the original IC tended to pull the D0 bit high, producing a 1. As a purely aesthetic concern, I've gone ahead and replaced IC21 here with a modern version of that chip. This means that if I examine an unmapped area of the address space, such as 0200, I'll now see all zeros. This change is entirely inconsequential to the operation of the machine, but is something I prefer from a conceptual point of view. I'm now going to power off and reassemble the computer, and when we come back, we'll look at another example program. In addition to the segment test program that we saw earlier, the manual here contains a number of other programs we can run on the computer. So let's have a little flip through and see what's available. Now here near the middle of the manual is an example sample number 5. And this is an interesting program as it's a number guessing game. The computer will choose a random number and we can choose some guesses. It will tell us whether we're too high or too low, and we can then go ahead and choose a different number until we get the correct value. So let's put the program to one side here and we can begin entering it on the computer. Now to enter it, we're going to use the auto functionality of the monitor, which allows us to specify a start address and will automatically increment the memory address as we're entering program bytes. Now you might notice that this program starts at 0060. So we press auto and we specify the start address 0060, and then it asks us what we would like to put into that piece of memory. And in this case, the answer is 7F. Then it moves automatically to 61, and then we enter the next bytes of memory. So in this case, 00, and at 62, 86. Then you can see we're at 63, and the next piece we need to enter is C6, and then at 64 to 0. Now I'm going to program this through in silence, and I'll speed up the video for you. And when we're done, we can try out the game. So I've obviously double tapped a key at this point. So what I'm going to do is step back a bit by resetting, and I'm now going to examine from A4 onwards. And we can see 4F, which is correct. We can go forward to C5B, which is also correct. Forward again for A0. And then for A7, we have 20. So this is incorrect. So 20. We can go forward, and this should be B7. And if we go forward here, we have 96, which is fine. And then 86, which is also fine. And then here we have AB, we should see 4C. So again, there's an error here. So what I'm going to do is actually I'm going to resume from here by using the auto, by starting the auto at 00AB. And from here onwards, we should have 4C. And then 9, 7, 8, 6, and so forth. Okay, so we've completed entering the program. Now, to get out of the auto mode, we can press reset. And if we remember, our program starts at 0060. So we need to start the program by using do 0060. And now it's waiting for a key press for us to see the random number. And let's press 8. Any number would have done. And now you see a decimal place has occurred, and this just tells us that it's now waiting for our first guess. And I'm going to choose 8. And it says we're too high. Now let's choose 0, and it says I'm too low. Now you see those are quite brief flashes, but if we look closely at the program code here, we can actually see how it decides how long to hold the display. And this is specifying with a number here, 6000, and that's our address 97. So what we can do is we can actually inspect the code and change this number to make it a bit longer. So let's go ahead and let's inspect from 96 to make sure we see our CE, and then we can change 6000 to something a bit longer. So let's reset to exit the program. We can examine 0096, which is our CE, and if we go forward, we see our 60. And here I'm going to change this to FF. I'm going to use the change key here, change FF. And now that's set in memory. So now we can restart our program by going reset and then do 0060, and our program started again. Now I need to, of course, seed that random number. This time let's press 0, and our random number is seeded. And let's make our first guess of 8. And now you see that display is much longer in duration. 8 is too high, so let's choose a bit lower, 5, and we guessed correctly on our second go. Now we can go ahead and press a key again to advance to the next position in the random number generator. There we go. Now we have a number to guess, and I'm going to guess with 8 again, and that's too high. 5, still too high. 2, still too high. And 0, and it turns out that 0 is the correct answer this time. Again, we can press a number, let's say 0, to choose our random number, again indicated by the dot here. And then we can go ahead and again, let's guess from 8. And in this time, we got it right first time. Let's try one more time. And let's start with 8 again. Too high. 5, too low, so somewhere between 5 and 8. So let's try 6, and that's our number. Okay, so I think this is a kind of fun little guessing game, and gave me an opportunity to show you how to enter the programs into the machine using the auto mode to make a correction, and then finally to edit the code as well to make some minor modifications. Now, entering these programs does take quite some time, so you might be quite reluctant to erase all that hard work. Hence the standby mode that allows you to preserve the memory. But if you'd like to enter another program, you might need to overwrite or erase the one you already have in memory. And that would encourage you to want to save the program out to some external device. Unfortunately, the ET-3400 doesn't support any way of saving to external memory by itself. However, Heathkit did release the ET-3400. That's not to be confused with the ET-3400A. Heathkit's naming scheme did leave something to be desired. The ETA-3400 is an add-on for the ET-3400. It includes additional memory and additional I/O capability. This includes a serial port for a serial terminal, but also a cassette interface to allow you to record programs to cassette tape and to play them back in again. In addition to providing that additional memory, it also includes additional ROM. Those ROMs provide a monitor program for the serial interface, allowing you to operate the device entirely from a serial terminal. And it also includes a version of Tiny Basic to allow you to run your own basic programs on the device as well. For me, I think the most valuable aspect is the ability to save those programs, and so that's something I'm definitely going to be investigating in future. But for now, I hope you found this video about the Heathkit Microcomputer Learning System, the model ET-3400, interesting, and I hope to catch you again soon in the next video.